So now I want to show an actual cell and talk about a few features and explain what their purpose is. So shown here is this 3-junction cell. So you have this top PN junction, which is the highest band gap. Then you have this intermediate PN junction, which is of a material which has an intermediate band gap, and towards the end you have this lowest band gap cell. So you'll see a few features over here which are present in each of these 3 cells. So you'll see that each of these cells has this window layer which is present on the top of each of these cells. And then it also has this back surface field. So at the bottom of each of these cells you have this back surface field layer. So there's this extra layer called back surface field layer over here. And then in between these cells, in between these 3 cells, you have these 2 tunnel junctions present, and these are very important for the functioning of this cell as well. And at the very top you have this anti-reflection coating present at the top. So these are 4 things I want to talk about, starting with the anti-reflection coating. So you guys will say, we just talked about anti-reflection coating. What's the big deal? It's the same anti-reflection coating, right? So the big deal is over here. So I had optimized this silicon nitride and the thickness of this silicon nitride. So take out that part that you just stored in the right part of your brain, and I had optimized this for a particular wavelength, right? So I had optimized it this reflectivity for a wavelength of, let's say, 600 nanometers. So I had my reflectivity maximum such that it was optimized for, let's say, this green light. But it was not, the reflectivity for this blue light or this red light was pretty high up here, right? And this was fine if I was using a single junction cell. But now I've designed this multiple junction cell where I've really optimized this cell, this top cell, to absorb the blue photons, and I have optimized this intermediate cell to absorb the green photons, and I have optimized this bottom cell to absorb these red photons. So now if I use, I can go ahead and put the same silicon nitride over here. But now I'm, basically I'm restricting, or I'm just reflecting the total supply of these lower and the upper cells, because I'm just using this one anti-reflective coating layer, which is really optimized for a particular wavelength. Where, as the whole purpose of using this multiple junction was that I want to exploit more of the spectrum. So I want to exploit my blue spectrum, as well as I want to exploit my red spectrum. But if I use that same dumb silicon nitride over here, it's reflecting back a lot of my blue photons, it's reflecting back a lot of my red photons, right? So you see the complexity increase over here, that I really want to use this anti-reflection coating such that it has a wider pass range, or it has a wider range of wavelengths across which it gives me a lower reflectivity, right? So the way to do that is to essentially add more layers to this anti-reflective coating. So instead of using one layer, what people do is they use a bi-layer anti-reflective coating, and it's usually made of things like, one of the layer could be Al2O3, the other one could be dioxide. Many times one of the layers is this magnesium fluoride, the other one is this zinc sulfide, and all of these are higher band gap materials, and they allow most of your light through, but you optimize the individual thicknesses as well as the refractive index such that you get a lower reflectivity over a large set of wavelengths. And I'm illustrating that using this figure over here. So this is for a bilayer. This is for a bilayer anti-reflective coating, where you have 2 of these layers, zinc sulfide and magnesium fluoride, and you can see that now you are getting this reflectivity which is staying low over a larger set of wavelengths. And you could essentially choose the thicknesses of these layers as well, such that depending upon whether you want to enhance your bottom cell or you want to enhance your enhance your top cell. So many times, when you grow these things, these cells might not be current matched, but you have now this extra knob over here. So maybe even if they are not current match, instead of let me squeeze the spectrum that they are receiving just by tuning this anti-reflection coating. So it's more complex to do, but it gives you can see the complexity rising over here, right? And sometimes people try to use 3-layer anti-reflection coating. I haven't seen more than that, but you usually use more than 1 layer for these multi-junction cells. Okay, is that clear? Okay, now let me talk about this window layer. So shown here are these 3 PN junctions, and at the top of each you'll see this thing which is denoted as the window layer, right? So the function of this is essentially contained in the name itself. So what is it's a window for light to come in. So it's like a window in your house. It lets the light in. It doesn't absorb any of it, but it protects the whatever is inside your home. It doesn't let dust in. It doesn't let particle inside to It provides a good thing, right? The window is a good thing. You stare out of the window. It's usually a good thing. So in the case of this multi-junction solar cell, the window layer, it lets the light in. So usually it's made up of semiconductor which has a larger band gap as compared to your PN junction. So let's say on the top over here you had a PN junction of, let's say, indium gallium phosphide, and now this window layer is made up of, let's say, aluminum containing indium phosphide, and this has a higher band gap. This has a higher band gap as compared to this PN junction layer. So it lets in most of this light in. The other advantage of using this window layer is that it provides a very good surface passivation. So now if you think about this PN junction which is between this indium gallium phosphide layer, the top surface of that is now essentially terminated by this window layer. So I have this window layer which is terminating the surface over here, and this usually provides, since this is a junction between 2 semiconductor materials, so this is an interface between one semiconductor which is crystalline and another semiconductor which is crystalline. So it's a very good interface, and the surface recombination velocity or the trap density at this surface are very low. So essentially it does 2 things. It provides a window, and it also provides a very good passivation layer. So as a result of that, these electrons which come over here, these holes which come over here, they are reflected back, and these electrons which come over here, they can tunnel through this small barrier over here, and they can be collected at this contact. So it provides a good selective contact. So it does it does quite a few things. It provides a good window. It provides the surface with the low surface recombination velocity, and it helps me realizing this selective contact, where I have this contact which is reflects back my holes, but it collects my electron, right? So, and again, I can do that because I'm growing these multiple materials on top of each other, and usually when I'm growing these cells, they are made of 3,5 materials which can be doped while I'm growing them. So I can essentially grow this one material on top of the other with a high doping while I'm making the cell. So I can utilize this good interface between these 2 semiconductors to give me this all the good things that are associated with the window layer. Okay, so window layer is clear. Okay, so a similar concept but slightly different realization is that of a back surface layer. So again, if you look at all these 3 cells, you see that the back surface or the bottom of these each of these cells has this layer which is termed as a BSF. So this again is a usually made up of a material which is a higher band gap as compared to your cell, and it achieves again the function that since this interface at the back is between two semiconductor materials, this is now oops, this is now an interface which has a good surface recombination velocity, and now I can make it selective to my hole. So I can dope this layer to be P plus, or I can dope it such that this band lineup between my cell and my back surface field layer is like this. So now my holes can easily be collected across this because they have this reduced barrier for tunneling. While this layer or this field at the back surface, it repels these electrons from this back surface. So again, it helps me realizing all those things. It helps me realize low surface recombination velocity at the back contact, and it helps me realize a selective contact for holes in this case. And also it's made up of a higher band gap material, so it does not really block the light from reaching the cell below it. So this back surface field layer, it won't really block this green photon from reaching my middle cell. Similarly, this back surface field layer over here is made up of a higher band gap as compared to what was used for this junction, so it will let these light to pass through. Right? So all these things are really important, and even though this design is complex, it allows you to essentially make these window and back surface field layers. So both at the front and at the back, you have these higher band gap materials which help you achieve a lower surface recombination velocity, also help you achieve good selective contacts. Right? So okay, now is the important thing. So why do I need this thing called tunnel junction? Okay, so I have these three diodes. Okay, so I have this top diode, right? This is a PN diode. I have this diode which is an intermediate cell. This is a PN diode. I have this third diode which is a PN diode. So these three diodes are connected in series. Why do I need a tunnel junction, or why do I need this fancy thing over here? Right. So can somebody explain why? Why do I need a tunnel junction? Okay. Do people agree with what he said? Let me give you some more visual aids. So I have this layer over here. So this is NP junction. Okay, and then I have this green cell over here. This is a NP junction. Okay. Actually, does somebody know what this device is? NP. It is taken 216. It's a thyristor. Anyway, this you're not supposed to know it, but it's good that you if you do. So, okay, so this is what you were saying. So now you can explain what were you saying again, just for everybody here. No, you can. I mean, you can repeat your argument. You can see it, or I just want everybody else to understand it. Yeah. So, sure. So now you see that you have this PN junction over here, right? Which is maybe biased in this way, right? So this is for current to flow. Let's say each of these is forward bias, right? So this junction is forward bias, this junction is forward bias, this junction is forward bias, right? But since I've grown these materials on top of each other, you see that there's another PN junction over here. right? So there's between these two there is another PN junction over here which is reverse bias, right? Similarly over here there is another PN junction which is reverse bias, right? So look at between this and between this. Do people see this? Right? So since I'm growing this PN, usually if you grow this PN, you'll think that you might get two junctions, but that is not the case. You get, so let's just step back a little bit. So let's say I grow two PN junctions on top of each other. So I not only get two junctions, but I also get a junction in between these two, right? And it's usually biased the opposite way. Right? So if these are forward biased, that other junction in between is reverse biased. Right? So it's going to block the flow of my current. Now it would have been much more simpler if you guys would have agreed with me and say let's put another terminal in between. Right? Maybe it would have been easier, right? But anyway, so I mean your choice, you have to deal with it. So now what do I do about it? Any idea? Yeah. Okay. So what Ben, right? Ben is saying is that let's put a layer over here and dope it really, really high, right? So high is P plus, let's make it P plus plus plus. And let's make this one N minus minus minus. And then hopefully my problems will go away. And let me explain why. Why doping these two higher would make your alleviate your concerns a little bit. Okay. So let's understand. What will happen if I dope these layers very very high. So I'm illustrating over here for this case between these two junctions. So I have this NP junction over here, and then I make this between, and then I have this bottom cell over here which is gallium arsenide. I have this top cell which is indium gallium phosphide, right? And now what I've done is connecting these two. I'm connecting them using these two layers, and I have doped each of them very heavily. So I have doped this layer to be very heavy p-type doping, and I have doped this layer to be n-type doping. And so, fulfilling your request, shown here is a band diagram for this. And what if you have a PN junction, right? So this would be your PN junction. Now, if you increase the doping on both your P and N side, now your junction becomes much more steeper, right? And if you increase it further, it would look something like this. So this is a very steep PN junction, right? And another way to look at this is to look at the depletion width. So the depletion width of this is very small. Okay, and if you make this depletion width very small, the carriers from one side of the junction can easily go to the other side of the junction, even though this is reverse bias, through the phenomena of called tunneling. So that's why this junction is called the tunnel junction. And so people who don't have, so to give you some more background on the physics behind this tunnel junction. So what I do over here is that I have this PN junction, and I dope this very heavily. So this conduction band over here is full of electrons, right? Similarly, I have this p-type semiconductor over here. So I dope this very heavily, which means this valence band is full of holes, or you have a lot of vacancies or absence of electrons in this band, right? Now if I dope this very heavily, another thing which happens is that the depletion width, that is the width or which explains the sharpness of this junction, is inversely proportional to the effective doping. I can define the effective doping like this. It's geometric mean of doping on both sides. So if I increase the doping on both sides, this depletion width decreases, And now these two bands between the N layer and P layer, they are very close to each other, because earlier it was a much larger depletion region. Now I have compressed it, I've reduced my depletion width, such that these electrons now, right, they can tunnel across, so they can go through this forbidden barrier into this valence band. So you see that there are a lot of electrons over here, and then they see, okay, there are empty states over here. So why not, just tunnel through it, right? So usually if you think of electrons, they love to travel down the hill. Okay, we have discussed this earlier. Holes love to travel down the hill. Electrons love to travel down the hill. Holes love to travel up the hill. So if you look at from the barrier point of view, right, this electron has a large barrier for going to the p side if it wants to go the conventional way. But I say, maybe if some way I can just tunnel through this barrier, right, and I can just go through this barrier, right? So instead of jumping through it, let me go tunnel through it, and I can land up inside the p layer, and that can happen when the doping on both these sides are very high, right? So when you dope this PN junction to be very high in a reverse bias state, you can still conduct current through it, and that's what negates this extra junction which arises between these PN junctions which are grown on top of each other. And also the peak current, so usually if you have a diode, you have IV characteristics which looks like this. So you have a forward bias region and you have a reverse bias region, right? And then when you bias it really high, you get this breakdown. But now since you have doped this very heavily, when you apply a low voltage, you can tunnel through this junction and you get a high current in your reverse bias, right? And the maximum amount of current that you can get in reverse bias is again proportional to the doping, or it's inversely proportional to exponential function of this doping like this. So the more doping you have, the higher the peak current you can get. So usually you want to dope these P plus and N plus layer as high as possible, and that would give you a peak current which is hopefully higher than the short circuit current of your cell. So all that current which was generated in the cell can tunnel through or pass through this tunnel junction without facing any extra resistance. Okay, so usually you want to maximize this peak current density of this tunnel junction and make it greater than the short circuit current density of your cell. Okay.